talk about some examples going the other direction by starting with 3 points. You probably learned in geometry that 3 points uniquely determine a plane. Let's look at the points 1, 2, 0. That's x equals 1. Here's on the x-axis, the y-axis, and the z-axis. To plot the point 1, 2, 0, you go 1 unit in the x direction and then 2 units here in the positive y direction, and now 0 in the z direction. So I'll call this point A. 2, 0, 2, that's 2 units in the x direction, 0 in the y direction, but then 2 units up in the z direction. There's point B. And point C is 1, 1, 0. 1, 1, 0 is just like 1, 2, 0, only way over here, C. So we have, here's the point A, the point B, and the point C. I could connect them to form a triangle. We're not so much interested in the geometry of that triangle, but you can imagine a plane that contains this triangle, and that's the plane that contains the points A, B, and C. You can see it's a weirdly slanted plane. How in the world are we going to get an equation for this plane? Well, remember, to find the equation, we need a normal vector n and 1 point, which we write in vector form as the vector r0. Of course, we have 3 points already. We can use any one of them as our 1 point. We'll just pick this one for r0 to be the vector 1, 2, 0. But how are we going to get n? How are we going to find a vector normal to the plane that we want? Well, here's our point A. It might be hard to see it in this picture, but look at this vector from point A to point B. This will be the vector AB, like that. And maybe I should use a different color for that, so let me... I lost my z-axis here, so I'm going to put back in the z-axis. But now I'm going to use green here. This vector is the vector AB, and in red you'll see the vector AC. So those two vectors are on the plane that I'm interested in, and I need a vector perpendicular to the plane, so it has to be perpendicular to both AB and this vector, the red one here, AC. How do I find such a thing? I'll use n to be the cross product, AB cross AC, because we know the cross product of two vectors is perpendicular to both. So what is the vector AB? The vector AB is the vector that goes from A, the point A, to the point B. We get the coordinates just by subtracting from the coordinates in B. We subtract the coordinates in A. So n will be this vector AB, which is the vector 1. That's 2 minus 1. 0 minus 2 is negative 2. And 2 minus 0 is 2. That's the vector AB. And we take the cross product of that with the vector AC, whose coordinates are 0. That's the 1 minus 1. Then 1 minus 2 is negative 1. And 0 minus 0 is 0. How do we find this cross product? Well, you learned the formula. The first coordinate in the cross product is this negative 2 times 0 minus 2 times negative 1, which is just 2. The second coordinate will be, and it's a bit tricky here, for the second coordinate we want, what is it? We want the 2 times 0 minus 1 times 0, which is just 0. And for the third coordinate, we'll get 1 times negative 1, this 1 times this negative 1, minus 0 times 2, and that will be negative 1. Now you can check in your head, is this correct? We might have made a mistake when computing the cross product. Is this vector really orthogonal to both this first vector AB and the second vector BC? In your head, do the dot product of this vector n with AB. 2 times this plus 0 times this minus 1 times that. Well, that's really 0. What about the dot product with AC? 2 times 0 plus 0 times -1 plus -1 times 0. That's really 0. So this really is a vector orthogonal to both of these vectors, AB and AC. And once we know n, and again, we're going to use this vector R0, which is the vector 1, 2, 0, we can write the equation for the plane just by writing the first coordinate of n, which is 2, times x minus the first entry in R0, that's x minus 1, plus 0, I'll write it here, 0, times y minus 2, minus 1 times z minus 0 equals 0, or that simplifies to 2x minus 2 plus 0 here, minus z equals 0, or 2x minus z equals 2. This is a very simple form of an equation for that plane. Now, once you've done all this work, is there a simple way to check it? The answer is yes. Every point on the plane must have its coordinates satisfy 2x minus z equals 2. Let me be clear, that's the number 2 here. Does this have 2 times the x coordinate minus the z coordinate equal 2? Yes. 2 times the x coordinate minus the z coordinate is 2. Yes. 2 times the x coordinate minus the z coordinate is 2. Yes. And if all 3 points lie in the plane, not only do things check out, but it has to be exactly the correct plane, since there's a unique plane that goes through those 3 points, A, B, and C. Now, using this type of trick, can we find an equation for the plane that goes through the points 1, 0, 0, 0, 0, 1, and 0, 1, 0? Let me show you where these points are here in the plane. 1, 0, 0 is here, 0, 0, 1 is here, and 0, 1, 0 is here. I'll draw the triangle connecting them, and imagine the plane that we're interested in, the plane that contains this triangle, so you get a good visual idea what that looks like. Is there a simple way to get the equation? Well, here's one really quick trick. The quick trick is, can you find some one linear equation that all 3 of these satisfy? If I just write the equation x plus y plus z equals 1, it should be immediately obvious that all 3 of these points satisfy this one equation. So bam, there's the equation for that plane. Now, if you didn't notice that, is there a way to figure that out? The answer is yes. If we call this vector A, this point A, this point B, this point C, we can use R0 is the vector, say 1, 1, 0, 0. That's just, I'm picking point A as my base point for the plane. And how will I find n? Well, just as before, I can take AB cross AC, where now AB is the vector -1, 0, 1, and AC is the vector -1, 1, 0. What's the cross product of these 2 vectors? Well, let's see. The first coordinate of the cross product is 0 times 0 minus 1 times 1. It's -1. The second coordinate of this cross product is also -1. I'll leave you to work out the formula. The third coordinate is also -1. And check, is this vector -1, -1, -1 orthogonal to both of these? Check the dot product with AB, you'll see immediately it's 0. Check the dot product with AC, you'll see it's 0. And so this is okay. So the equation for the plane is just given by taking the first entry from the normal vector multiplied by x minus the x coordinate of our base point, minus y minus 0. So minus 1 from here times y minus 0. Then we have a minus 1 times z minus 0 equals 0. If I multiply the whole thing by minus 1, I get x minus 1 plus y plus z equals 0, or x plus y plus z equals 1. It's okay to leave the equation like this. There's nothing wrong with that. But it also looks like this. It's just an equivalent way of writing the equation, which is what we had guessed right at the beginning.